At Engineered Air Balance, you can feel the difference. We are a leading authority in total system balancing and building commissioning at the forefront of industry standards and training. The difference is our comprehensive approach to total system balancing, which continues to advance the industry's benchmark. The difference is our expertise in building commissioning, which encompasses HVAC, electrical, plumbing, and life safety. The difference is our state-of-the-art training center located in Houston, Texas, where we are uniquely equipped to train the next generation of technicians. And finally, the difference is our team, whose technical knowledge, unmatched thoroughness, and continuous reliability sets us apart, allowing us to deliver an optimum operating facility. To learn more about how we can make a difference for you, go to eabcoinc.com.
Good afternoon, everyone. Just wait a moment before Justin gets his presentation up. Thanks, Justin. Well, welcome everyone to our first webinar in AABC's Tab Talk series. Thanks to all of our members and also non-members across the community for participating today. And a special thanks to Engineered Air Balance for supporting this webinar. I have a few Zoom notes before we jump into things today. If you have questions for our speaker, please use the Q&A button in your Zoom window, not the chat box, and we will feed those questions to our speaker at the conclusion of the presentation. You can submit questions at any time, so there's no need to wait until the end. If you have technical issues, please use the chat box to inform us and we can assist you. So jumping into things, today's presentation is Electrical Distribution Systems, what a TAB professional should know, with ABC member Justin Garner. Justin leads the Houston office as Vice President and Branch Manager of EAB and has over 18 years of experience in building commissioning and testing, adjusting, and balancing of HVAC systems. He's also an active member of ASHRAE and currently serves as a voting member of the committee that manages all of the individual standards and guidelines pertaining to building commissioning. Justin also chairs the ACG Certification Council and is a frequent technical contributor to ABC and ACG. So without stealing any more time today, I'm going to hand it off to our expert to kick us off. Justin?
Wonderful. Thank you so much. And thank you everybody for joining us today. I guess I would say good afternoon, but depending on where you are, it may still be morning. But thank you for taking time out of your day to join us. And I hope that the information that we're going to present today is worthwhile for everyone. So we'll get right to it. All right. So a few of the learning objectives today. We're mainly going to talk about electrical distribution systems as they apply to the TAB profession, and try and give some broader based knowledge to TAB professionals. I find in our own company that many of our TAB guys, they understand electrical power, they understand how it relates to the measurements that we take, but they don't necessarily understand the bigger picture in a building, whereas our building commissioning side of the house, obviously has some very detailed knowledge in that area. So we're going to try and give a high level overview of that and touch on some unique skills that through our training courses we've identified may not be as widely known related to motors as well as brake horsepower measurements and things like that in the industry. So we'll get right to it. I'm going to start out by just talking about different types of power distribution systems. This first one that we're going to discuss is what you would typically have in your home here in the United States and probably throughout North America. But this is a 120, 240 volt single phase 3-wire system. And you may say, well, it's single phase. Why are there 2 wires? And so, because it's interesting, the way that this is produced, and give me just a moment here, I'm going to pull up my laser pointer so I can help explain some of these things. But you'll notice here you've got a hot leg here, and a neutral in the middle. And the way that this is derived is the utility essentially just gives you 2 legs and a neutral, and it's a split phase. So these 2 legs are 180 degrees out of phase from one another. which is obviously very different than a three-phase system that we're going to talk about next. But in this type of system, which, as I said before, you would primarily find in residential or light commercial applications, you're typically going to have 240 volts differential between the two ungrounded conductors, as we would call it. And then your neutral is considered by the National Electrical Code to still be a conductor, but it's a grounded conductor. And that means that it's tied to ground at its source, typically at the service entrance to your facility or to your home. And so between the ungrounded conductors and the grounded conductor, you're going to have a voltage potential of 120 volts. And so that's how these systems are derived. And that's what you would notice, like I said, in most residential applications. Moving on to our first commercial system. This is what we see in 99% of commercial facilities out there. Obviously any modern facilities, some older facilities may have a different arrangement, but we're going to talk about what we see in most facilities. And that's a 277 480 volt, three-phase, four-wire system, a Y-connected system. You will see at times a three-phase delta connected system, and it's just a different transformer arrangement, and you will not have a neutral here or a grounded conductor. You'll only have your three hot legs. That's about all we need to talk about in this presentation in that sense. But the vast majority of the time in most commercial applications, we're going to see this application because we use this 277 volt component or the single phase component of this power system for various things like lighting and smaller electrical loads on the HVAC side, such as electric duct heaters, maybe fan powered boxes, terminal units, and things of that nature. That still may draw too much amperage to put on a 208 120 system, which we'll talk about next, but obviously don't need full three-phase power. And so what's interesting to note here, again, is we have three ungrounded conductors. So we have a phase A here, phase B, and a phase C. I have these color-coded the way that you can see them in the field, but you may see other colors. It's important to note that you should have three distinct colors there, and then typically in this system, a neutral would be gray as opposed to white. But the code only stipulates that they be distinct colors and used uniformly throughout a facility. So when you start looking at wiring colors and things like that, just be careful and make sure you understand the type of system you're observing, and really if there's any question at all, safety first, and check your voltages with a meter, which we'll talk about a little bit later on. So I'm going to go ahead and move on to the next system. This is the step down in most commercial facilities, and when I say step down, I'll explain that in the next slide. But this is when you typically come into a facility at 480, 277 volts. And that's what would feed most of the larger equipment, lighting, things like that. And then you're going to have transformers that step that voltage down to a 208 120 system to feed smaller equipment and mostly your plug loads and things like that within the facility, and maybe a myriad of other things. But normally this is just plug loads and maybe some smaller HVAC equipment if you have some single phase fans. Or things of that nature, you may have that fed off of here. One thing to note here, if you have some smaller HVAC equipment that may border on the residential, real light commercial side, and it may be dual rated for a 230 or 240 volt or 208 system, the way that would be connected here would be between two of the ungrounded conductors within this system. So if you see a motor, and we're going to talk more about motor designations and things like that as we go through the presentation, but if you see a motor that's rated at 208 to 230 volts, and you have a system like this, well, you can't get 230 volts out of this system, but you can connect that motor to two legs of a 208 system, and it will operate. Understand it's going to operate at a different amperage, and we'll talk about that in a little bit later on, and it's you may have to wire the motor differently for it, but that's going to be manufacturer dependent. So just be aware of that. And then obviously the voltage potential between any ungrounded conductor and the grounded conductor is going to be 120 volts. You notice here that these are color coded differently. Most of the time in a commercial facility, you will see black, red, and blue used on the 120/208 side of the power system. And typically your neutral will be white. But again, always double check that, because the code doesn't stipulate that they have to use a certain color. It just stipulates that it has to be unique and used uniformly throughout the system. Okay, so we're going to get into the nuts and bolts of an actual electrical distribution system. And this particular drawing here is from a high-rise basic sciences research building. So it's very, very power intensive. At first glance, it probably would look rather complex, and to some extent it is, and rather confusing to somebody that doesn't know what they're looking at. So we're going to break it down into pieces and go through each area and try and explain from start to finish how we distribute power, especially in a large facility, because this facility really has just about anything that you would see in a large commercial facility. So we're going to start here with the point of utility connection. And if you notice here, we have some underground feeders. In this particular facility, they were being brought in from a utility vault directly from the utility. This happens to be medium voltage switchgear. It was 4160 volts, or 5 kV is kind of what they're normally referred to. But it could be any range of medium voltage. I mean, depending on where you are and the utility company in your area, I mean, this could be all the way up to 15,000 volts or even more. But normally you're going to see somewhere in the range of 4160 up to 15,000 volts coming in this type of scenario. It's important to note that a medium voltage system is anything between 1,000 volts and 100,000 volts. So normally you're not going to see high voltage, which would be that next level up, as a direct feeder into a commercial facility. Industrial, yes, you might see that, but not in a commercial facility. And then typically you're going to be stepping down this medium voltage fairly quickly. But in the instance of this particular facility, being a high rise and a very large facility, they use the medium voltage to distribute power so that you didn't have as much voltage loss, and the wire sizing could be decreased to get power to the areas of the facility. And I'm going to show that here a little bit more in just a moment. In this particular facility, it's interesting to note, obviously with it being a lab facility, a lot of critical research happening in this facility. We have a very large emergency power system. And so this is something that you would need to pay attention to in any facility out there, but really one more of a critical nature. You're probably going to have some sort of alternate power source. It may be a second feed from your utility. It may be generators as we have here, or it may be UPSs, which I'm going to talk about in a moment, things like that. But it's important to understand, if you do have multiple sources, what is being fed potentially by dual sources. And I'll talk about that a little bit more in a bit, why that's really important. But just recognize here that we have generators being paralleled, meaning that they are feeding into a common piece of switchgear that controls them and makes them all get in sync or parallel. And then that's distributed out. And you'll see here, and I'm going to show you another picture later on, but this is an automatic transfer switch. These are the workhorses of these types of systems. And this particular ATS is fed by two emergency sources, as noted by the red feeders coming in. And then obviously it has a distribution feeder going out to this distribution panel here. You're going to see some of the other ones I'm going to show you will actually be fed by a normal source and an emergency source. And that's more likely what you would see in a typical commercial facility with emergency power. So we're going to jump all the way up to the top of this facility. This happened to be up on the 13th floor in the penthouse. And we're going to talk through some of these items here and how they relate to the HVAC systems. So this is a large piece of normal power switchgear. Your orange conductors that you see coming in here, coming in from that 5 kV medium voltage switchgear that we showed earlier. You notice you have an A and a B side. So we actually have redundant feeds there. There is a tie here in the middle that is normally open, but if one of these were to be lost, that tie could be closed and this entire gear could be fed from one side or the other. That's very common in commercial facilities these days. Usually doesn't affect things that we do on the tab side very often, but it is nice to know what kind of sources you have and things like that. You'll notice here that anything that's in green is normal power only. It would only be fed from a utility source. So it's not tied to the emergency system, whereas we see our ATS here that has a normal source here, and then it has an emergency source coming from that paralleling gear that we showed earlier, feeding into this ATS. The way that these ATSs work is they're going to monitor their primary source, which in this case happened to be the utility source. If they see that source fail, is not present anymore, then this ATS is going to send a signal down to the paralleling gear that controls the generators, or maybe directly to the generator itself, and it's going to tell that generator to start and that it needs power. And then as soon as that generator starts and it's up to speed and generating power at the right voltage and frequency, then this ATS will automatically transfer to this alternate source and then thus provide power to this distribution panel and anything downstream. So that's kind of how the emergency power and utility power tie together in a very simple sense. It's interesting to note that most large HVAC equipment in buildings is fed typically out of distribution panels. So you're normally going to have a piece of switchgear. It's going to have larger breakers. Normally these are in the 400 to 2000 amp range. In a central utility plant, you might feed a large piece of equipment like a chiller or something very, very large like that directly off of a breaker in a piece of switchgear. But normally it's going to be distributed down to a distribution panel. In this particular case, these distribution panels were feeding some large air handling units. I think we had 80,000 CFM air handling units in this facility, 100% outside air. And we had very, very large laboratory exhaust systems. So these systems were feeding those. Some of them were on emergency power, some of them weren't. But I'm not going to get into that too much. The other thing that you're going to see here is you're going to see this transformer. So what's happening here is this is at 480, 277 volts, like we showed earlier. And then this is a step-down transformer, which takes that down to 208, 120. So this panel right here would be 208, 120 volts, as we talked about earlier, whereas this is 480, 277. All right, we're going to move down the building now, and this is a high-rise building. This is pretty typical. So all the electrical rooms are stacked on top of each other as you go up the building. And so they use this bus riser, which is just a very large conductor that can be used to distribute power throughout the building. And in this particular case, this riser ran vertically up through all the electrical rooms, and it has plugs that plug into it. So that's what you see right here. And then coming off of that is additional distribution panels. So in the case of this view right here, this I think served the office area of this particular facility. And then we had lab wings as well. So obviously this is only being served by normal power, so it's not as critical as say maybe the lab areas. More than likely, these panels were serving fan power terminal units and other 480, 277 loads. And then you'll see here that we have a transformer that takes everything down to 208, 120. We have a distribution panel here that's feeding out to panel boards. And panel boards are most like what you would recognize in your home that distributes power within your home or another light commercial facility. These are intended to get down to branch circuits, as we call them. Your typical 15, 20, 30 amp branch circuits that would feed lighting and plugs and much smaller loads, whereas your distribution panels will typically feed higher amperage loads. And these can run, typically these panels are going to be anywhere 100 to 200 amp, maybe a little higher, maybe a little lower, but that's pretty typical. So it's just important to understand from a tab standpoint, what voltage system is your equipment fed from, and then understanding where that source may be. And oftentimes, and the code mandates it that everything kind of be labeled. But you should see circuit labels in various forms on equipment. And so you need to understand, you may be going back to a panel board, you may be going back to a motor control center, maybe going all the way back to a piece of switchgear. if you needed to go find the source of that equipment. And so that's kind of what we're trying to show here today. All right, I'm going to talk about this particular system here. It's interesting to note that when we start talking about controls, if you have any experience with large control systems and large commercial facilities, and especially ones that have emergency power, you know that can be a bad combination. It can cause problems, especially when you start switching between normal and emergency power. It can really throw building automation control systems out of whack, and as well as networking and IT systems. And so what you're normally going to see is some type of UPS. Typically, your networking systems are almost always served by UPS or uninterruptible power system, which is basically a battery backup to where you don't ever have a blip. It will seamlessly switch from battery power through an inverter over to the utility or the emergency source that's feeding it. And that's what we have here in this particular instance. We have an ATS that's actually fed by two emergency sources, feeding into a UPS, which is this module here with its own distribution panel. This particular model actually had a transformer built in that stepped down to 208. So these are 208 120 panels that are being fed out of this system. And this fed the entire IT infrastructure as well as all the controls in the facility. So it was a really neat setup. We didn't have a lot of the issues with cycling of control panels and things like that. It can cause some other issues. Obviously, the BAS has to know when power is cycling, so it doesn't see equipment that may not be on UPS go down. But that's a conversation for another day. Just recognize, though, that you need to identify whether the systems are uninterruptible or not. All right. One other concept I want to cover before we proceed a little bit further is transformer theory. This is something that I'm sure most tab professionals understand. You have transformers. You have a voltage coming in, you have a voltage going out. But this is critical to not only distribution of power within a facility or in power systems, but it's also a critical concept to understand when we start talking about electrical motors, which is what we're going to get into next. But the governing principle here is called Faraday's law. And what Faraday's law basically says is that this EMF is generated in between a primary source and a secondary source, and that's essentially what through flux and magnetic fields transfers the same amount of energy with some minor losses and things like that because of the material over to the secondary side. And so essentially what you have when you simplify all this is this equation right here. And so this is the voltage of the secondary divided by the voltage of the primary is equivalent to the number of turns or number of wraps around this core of the secondary versus the number of the primary here. And so if you know the number of turns, that dictates the secondary voltage versus, compared to the primary voltage. And this is essentially how transformers in all commercial facilities work. I don't want to go too far down in the weeds, but if you open up one of these transformers, and I guess I probably should have put a picture in here of that, but I didn't. You have different settings on those transformers for the secondary side. They're called tap settings. And so you can essentially step the voltage up or down, or the electrician can, excuse me, and to get the right voltage based upon what's happening on the primary side. So you may have a utility that's feeding in a very high voltage, and you may have a secondary that doesn't have a lot of load on it, and so you may need to step that down a little bit, or vice versa. And so that's something that the electrician has to look at, and we look at sometimes on the commissioning side as well, to get the appropriate secondary voltage on the downstream side of these transformers. So the next thing I'm going to do, I'm going to play a short video here, and I apologize for kind of pawning this off to a video, but this video does an outstanding job of explaining how an induction motor works, much better than I can do. So I would appreciate it if you try to stay awake, and hopefully this is informative.
Induction motors are the most commonly used electrical machines. They are cheaper, rugged, and easier to maintain compared to other alternatives. In this video, we will learn the working of a three-phase squirrel cage induction motor. It has two main parts, stator and rotor. Stator is a stationary part, and rotor is the rotating part. Stator is made by stacking thin-slotted, highly permeable steel laminations inside a steel or cast iron frame. Winding passes through slots of stator. When a three-phase AC current passes through it, something very interesting happens. It produces a rotating magnetic field. To understand this phenomenon much better, consider a simplified three-phase winding with just 3 coils. A wire carrying current produces magnetic field around it. Now, for this special arrangement, magnetic field produced by three-phase AC current will be as shown at a particular instant. With variation in AC current, magnetic field takes a different orientation as shown. From these 3 positions, it's clear that it's like a magnetic field of uniform strength rotating. The speed of rotation of a magnetic field is known as synchronous speed. Assume you're putting a closed conductor inside it. Since the magnetic field is fluctuating, an EMF will be induced in the loop according to Faraday's law. The EMF will produce a current through the loop. So, the situation has become like a current-carrying loop is situated in a magnetic field. This will produce magnetic force in loop, according to Lorentz law. So, the loop will start rotating. A similar phenomenon happens inside an induction motor also. Here, instead of a simple loop, something very similar to a squirrel cage is used. Three-phase AC current passing through stator winding produces a rotating magnetic field. So, as in the previous case, current will be induced in bars of squirrel cage, which is shortened by end rings, and will start rotating. That's why it's called an induction motor. Electricity is inducted in the rotor by magnetic induction rather than direct electric connection. To aid such electromagnetic induction, insulated iron core lamina are packed inside the rotor. Such small slices of iron make sure that eddy current losses are minimum. This is another big advantage of a three-phase induction motor. It is inherently self-starting. So, you can see here that both magnetic field and rotor are rotating. But at what speed will the rotor rotate? To obtain this answer, let's consider different cases. Consider a case where the rotor speed is the same as the magnetic field speed. Since both are rotating at the same speed, the rotating loop will always experience constant magnetic field. So, there won't be any induced EMF and current. This means zero force on rotor bars. So, the rotors will gradually slow down. But as it slows down, rotor loops will experience a varying magnetic field. So, induced current and force will rise again. And the rotor will speed up. In short, the rotor will never be able to catch up with the speed of the magnetic field. It rotates at a specific speed, which is slightly less than synchronous speed. The difference between synchronous and rotor speed is known as slip. Rotational mechanical power is transferred through a power shaft. In short, in an induction motor, electrical energy is entered via stator and output from motor. Mechanical rotation is received from rotor. Energy loss during motor operation is dissipated as heat. So, a fan at the other end helps in cooling down the motor.
Okay, I hope you guys were able to stay awake during that, but and found that informative because they can do a whole lot better job of explaining that with those graphics than I can. So I hope that was beneficial for you guys. Back to motors. So I want to talk about NEMA. Hopefully everyone in the tab profession at least has heard of NEMA because there are many different NEMA designations. NEMA is the National Electric Manufacturers Association. And like I said, among other things, because they are the ones that pretty much standardize all the products on the electrical side of the world, they standardize motor construction. And so it's important as tab professionals when we're collecting data that may be used by other contractors, may be used by engineers or building owners, that we write down the pertinent data or record the pertinent data within our reports that can be used later on if a motor needs to be replaced or it needs to be upsized or some other accessory needs to be added to that motor. And so some of the most important things, we'll talk more about this in detail at the next slide, but motor shaft sizing, frame sizing, and the electrical characteristics of the motor. If you've ever got to replace a motor and you call a supply house, the things they're going to need to know is they're going to need to know what's the horsepower of the motor, what's the frame size of the motor, what's the voltage that you need, and things of that nature, as well as the speed. And so all those things kind of tie into these, NEMA designations and standardizing to some extent the motors out there that are in the industry. All right, so let's get into some actual practical skills here, and let's talk about what we need to be collecting when we're out in the field and we're looking at electrical motors. And so I've got a kind of a graphical representation here of an old school data form. And so you can see that we have a nameplate column, we have an actual column here, and we're looking at a nameplate of a motor. So our manufacturer in this particular case is Baldor. Baldor is a very well-known motor, very popular in the HVAC industry, among many others. We've got a horsepower rating here of 5 horsepower. The frame size is 184T. Again, this is that NEMA frame size rating that standardizes. A frame size will dictate the shaft size of a motor and some of the other physical dimensions of the motor as well. So it's important to note that frame size. Obviously, we need to know whether this is a single phase motor or a 3-phase motor, because very different in terms of wiring and things like that. In North America, typically we're going to operate under 60 hertz power, at least utility wise. And but it's interesting to note that many of the motors you see out in the field today can operate at 50 hertz or 60 hertz, and there will be dual sets of data there. And so it's very important for the technician in the field to pay attention and make sure that they collect the data that's for the 60 hertz operation and not for 50 hertz operation. In this particular case, this is a 1750 RPM motor. We see RPMs that range, much lower than this, all the way up to 3600 RPM, depending upon the number of poles in the motor. In this particular case, we're on a 460 volt system. You see that this motor could operate on a 230 volt system as well. So again, it's important to understand, as we talked about at the beginning of this presentation, the power distribution within the facility and what the expected voltage is for this particular system and this motor. And then obviously, you have to know that voltage because it's going to determine the amperage. If we were 230 volts on the feeding this motor, we would have a nameplate rated amperage of 13.2 amps. But because we're using a 460 volt system here, our rated amperage is 6.6 amps. All right. So we're going to go into now a little bit about electrical instruments and measurements in the field. You can see here, I'm going to talk about safety here in a minute, and I'm going to reference back to this this picture here of this person that looks like they're in a bomb suit here. But this is some arc flash protection clothing, and so I'm going to talk about that here in just a moment. And then we've got just a few other pictures here. These are current clamps that we very frequently use. This is a smaller size. You see some larger coil type clamps here that we use with a power meter. I'm going to talk about that here a little bit more in detail. But just recognize when I say an amperage clamp, these are the types of things that we're referencing, and hopefully everyone that's out there doing tab work knows what I'm talking about. Okay, so anytime we start talking about taking electrical measurements in the field, we need to be concerned with safety. One of the most dangerous things that we do as tab technicians out in the field is take live electrical measurements. We don't have the luxury of turning off the power. We have to measure, electrical measurements while equipment is operating. And so it's very, very important that we train our personnel in the hazards of taking those electrical measurements and good solid safety practices. NFPA 70E is the standard that dictates electrical safety in the workforce or in the workplace. And so if you're not familiar with that standard, I would highly encourage you to go and study that standard, maybe get some training in that area. But NFPA 70E dictates the PPE that's needed. Mostly that is voltage rated gloves, eye protection, ear protection, head protection. And then obviously if there's an arc flash hazard, then you may have to wear protective clothing as well that's rated for those types of hazards. So well beyond the scope of this presentation to go into that. AABC has actually done some presentations previously on that. If you have any questions about that at all, I encourage you to seek out that information and that knowledge so that you can stay safe when doing this out in the field. One thing that we mandate in our company, and we think it's a very wise practice, is to always have an additional person present when you're taking live electrical measurements. It's just in case there was a safety incident, something happened, you can always have somebody there to react, but more importantly, it's a safety check as well. You can have a second person there just to make sure the person that's taking the measurements is following all the right protocols and obviously can try to be safe, because ultimately at the end of the day, that's what we want. We want everybody to be safe doing their jobs. A couple of other things just to note: the clamp-on device or the amp clamps that I showed you a picture of earlier, they need to have adequate space to fit completely around the wire. Oftentimes we get into very crowded or very tight electrical wiring compartments trying to measure amperage or voltage. And it's important that you can get a good solid clamp around those wires. Otherwise, you can have a false reading on your amp clamps. Another thing to note, and this is something that I would venture to say a lot of folks do not know, but we're seeing a lot of VFDs in the HVAC world today. The energy codes are driving it, manufacturers and engineers are pushing it, and they're great. They make our life a little easier sometimes on the tab side versus the old days of constant volume, shiv and pulley driven systems. But it's interesting what these VFDs do to the electrical signals going to the motors. And again, that's kind of another presentation, but you've got to recognize that the signal coming out of a VFD is not a true sine wave like you would get from the utility. It's a manipulated DC generated sine wave. And so to the motor, it looks like a sine wave, but to our meters, it looks like a very, very chopped up signal. And so what will end up happening is your meter, if it's not true RMS and it doesn't have a high pass filter for this application, will read very differently than what the motor is actually seeing. And what we oftentimes see here, if the filter is not engaged, is you'll get very high readings, especially if you're not close to 60 hertz and you're not close to full load amperage on the motor itself. Or off the drive, you'll get 520 volts on a 480 volt system. You just get some very off readings that would normally cause you to question the power system, but in this particular case, it would be an error on the part of the meter itself. So be aware of that and do some more research if this is new information to you. I'm going to show you a couple of meters that we use here. This Fluke 87V is our standard meter here at EAB. And we like it because it's a fully functional multimeter, but it has that low pass filter. And so we don't have to worry about taking voltage downstream of a VFD. We can just turn that filter on and we get good clean measurements, among other things. This meter can do a full suite of measurements for amperage, voltage, resistance, you name it, it can do it. Another thing that we do use on occasion, but not very often on the tab side, is a three-phase power analyzer. If you have to measure power directly, and we do have to do that sometimes, you're going to need a device like this, and it essentially measures all three phases of voltage and potentially even the neutral as well as all three amperages at the same time, and it gives you a full picture of the power that's feeding a particular piece of equipment. And so, like I said, it's useful, but it's not something that would be used every single day. All right, I'm going to talk about volts and amps just in terms of mechanical systems here. If you're new to this kind of stuff, Oftentimes we understand how mechanical system works when we talk in terms of flow and pressure on the tap side a lot. So what does that mean from a voltage standpoint? Well, if you're looking at voltage, what you're looking at is the differential between 2 points. And so what you're really looking at is pressure. So voltage is equivalent to pressure or head in a air or water type system. So if you're looking at across an orifice like we would have right here, you're going to get a pressure drop. Oftentimes we look at that in a water system to try and determine flow. It's kind of the same thing on the voltage side. You're looking for a voltage differential, and it's equivalent to the pressure in the system or the potential in the system. And it's interesting to note that you're always going to connect a voltmeter in parallel with the, either the ungrounded conductors in the system or between the ungrounded and the grounded conductor, if that's what you're looking for, because you're looking for voltage differential there. Amperage is the opposite. Amperage is flow. And so if you were to look at a pumping system like this, you would need to, just like if we were to measure volumetric flow rate in a hydronic system, we're going to need to insert a meter that actually measures flow inside the system in parallel with the flow, right? You're going to have to do the same thing with an amp meter. If you were to directly measure amperage in a circuit, you actually have to split the circuit and measure across it with your meter. That's not exactly how our current clamps work. They use a transformer type principle with a coil to do the same thing, but you are measuring in series in the circuit. I think I said parallel earlier, but it's actually in series. So just be aware of that. All right, so let's get into electrical calculations here. I'm going to breeze through this because I'm running a little long at the moment, but this slide gives you some of the common formulas that you need to know when we start talking about amps, volts, and power. Okay, and when we talk about power here in the United States, we typically refer to horsepower. Horsepower is 746 watts equals 1 horsepower. So just be aware of that. One thing that's interesting to know, I'm not going to go through each one of these in great detail, but oftentimes folks think in the commercial world, well, I just multiply volts times amps and I get power. Well, that's true in a single phase system, but it's not true in a three-phase system. And you need to make sure that you're accounting for the 3 phases or the square root of 3, which ends up being 1.73 when you're accounting for that. And so you've got to make sure you add that in here when you're doing that basic calculation. We're going to go a little bit more in detail into this though in the next few slides. All right, so we start talking about brake horsepower. Brake horsepower is the actual operating point at any point in the system. So we have a 15 horsepower motor connected to a fan. More than likely, you're not going to be at full 15 horsepower when that fan is operating. You may be, but usually we operate at somewhere less than full load amperage. Sometimes we operate above full load amps. But what we're talking about here for the purposes of estimating brake horsepower is the assumption that we're not at 100% load. And so for that, we have to account for the fact that we're somewhere between what the motor would be doing amperage-wise and power-wise with nothing connected to it, and what it would be doing if it were fully loaded. And so that's the whole purpose of this next round of calculations, is to help you understand that. And so as we go through here, we're going to be talking about some terms and things like that, but I'm going to get more into that in the next slide. All right. So we start talking about estimating brake horsepower in 3-phase systems. I gave you this constant earlier, but brake horsepower is watts divided by 746. We talked about why that is, but this is the formula that we're going to be using. And it's essentially 1.73, 3-phase system. This is operating or running amps, running voltage. This is full load efficiency times power factor. And this is essentially dictated by the motor construction itself and the operating point at the time that you're measuring it in the system. I'm going to talk a little bit more about this in detail here in a moment. And then this L is something that's usually forgotten or misunderstood, and we're going to try and dispel those myths today. But this is a load factor. And so this is a factor to derate this right here based upon the motor not being at full load conditions. And I'm going to show you how that plays in as we go through and talk about these calculations. It's interesting to note, though, we can measure running amps, we can measure running volts, and again, we always take the average of our measurements there. I'm going to show you how to calculate this, and I'm going to show you how to get this so that we can ultimately estimate our brake horsepower. So over here, if we need to try to figure out our full load efficiency times power factor, because it's not something you can always get off the nameplate, and certainly not the power factor. That's something you have to typically measure in the field. But you can estimate it. You take your nameplate horsepower times 746. We're converting it back to watts there. And then we divide it by our 1.732 times our nameplate amperage times our nameplate of our voltage. And this is going to give us our nameplate value for this, which is what we need for this calculation. Then the next component, we're going to need to estimate our percent loading. And to do that, we're going to have our operating or test amps. This is our average amperage that we measure, our nameplate amperage, and then our no load amperage. And you're going to say, where do I find my no load amperage? Well, I'm going to show you that on the next slide. That's something that the manufacturer does publish for the motor, so you might have to go look it up if you're concerned about that. Or, I guess you could, if you have the ability to unhook the motor and run it with nothing connected to it, you could get it that way. But this is normally not on the nameplate. So you may have to do a little extra work to get this value. Same thing here. This is your test voltage and your nameplate voltage, like we talked about earlier. And then we have this L factors table. This is an L factors table that's published in the AABC Technician Training Manual. It might also be in the national standards. It's a condensed version. There are some that are out there that are very, very detailed and that break down, almost every single percentage. And so you don't have to go through here and interpolate and things like that. But for the purposes of this calculation, we're going to use this table. And we're just going to estimate and go to the nearest L factor that's shown here and not try to do any crazy interpolation because it really doesn't make that big of a difference in the end. One thing to note, though, as I was talking about earlier, this L factor doesn't matter at 100% load. So if we're fully loaded, you can see it's 1, it's negligible. So this is data from a manufacturer, from Baldor, for this particular 15 horsepower motor. We're going to use this in the coming example. But you'll notice here at 0% load, we have a power factor of 6 and an efficiency of 0. And we don't really care about the speed at this point, but you'll notice that the speed does change. But our amperage here is 6.37 amps. Whereas if we jump over here to 100% load, obviously you can see our power factor and our efficiency have changed. And our amperage now is 17.7. So this formula that we're talking about, and really that L factor, is trying to help us bridge the gap between this number and this number right here when we start talking about percent loading. So let's go into an example here. We've got some data down here that we collected out in the field. It's for that motor that we just saw the data from Baldor. It's a 15 horsepower motor. Nameplate amperage is 17.7 amps at 460 volts, 3-phase motor. You can see we collected 12.5, 12.5, 12.5, so an average of 12.5 amps. Our voltage was an average of 477 volts. You can see we've got our L factors table down here, and then we've got this data that we pulled out of our Baldor manufacturer's data there. So what does this look like when we plug it in? So there's our formula. And so once we do all the math on this, we come up with the fact that we're about 56% loaded on this motor. That's not what you would get from common thought. You would, I know some folks that would look at this and go 12.5 amps out of 17.7. Well, that's about 60 something percent, right? Well, it's not. It's 56% because we're looking at the difference between no load and full load. And so it's very important that you run this calculation here. So with that being said, we would take this 56%, look down here at 50% on our L factors table, and we would use 0.909 as our L factor in the next equation. And so we're going to go through and look at this right here. This is the equation I showed you earlier. We're going to first calculate our full load efficiency times power factor, which is going to give us a 0.794. If we plug everything in there, that's pretty simple, all nameplate data. And then we're going to run our brake horsepower calculation, which will plug our 0.794 in from here. using our 50% load, 0.909 here, run the calculation, it gives us a brake horsepower of 9.99. It's interesting to note that if you did not use this extended formula and you did a very abbreviated version of this, you're going to get a little bit higher horsepower here. And so it is important to correct this down using the full load efficiency and your L factor to get it close, especially when you're in a part load condition. And again, here we were about 56% loaded. All right, I think I ran a few minutes over on time, but I appreciate everybody's time today. I hope the information was beneficial and everyone learned something. At this point in time, I'll ask Sam to send me any questions that may have come through as I was talking.
Thanks, Justin. Oh, we have a couple questions in the queue, and for those in the audience, if you have any questions, please feel free to submit them to the Q&A button. These two are semi-related, so let me read them both at the same time. Which is a more accurate reading, the reading of VFD or a true RMS meter? And then the second question was, how accurate are the VFD display readouts for amps and volts?
Those are very good questions, and you're right, they are very similar. And this comes up in just about every class we have where we start talking about these things. So I'm glad it came up in this particular discussion. I've talked to numerous drive manufacturers, all the major ones that are out there, and they all claim that their VFD readouts are more accurate than our meters that we would use in the field. And they may very well be correct. So with that being said, you should be able to look at those displays and they should be fairly accurate. What I tell the folks that work in our company and anybody else that really asks me this question is, we as tap professionals have an obligation to measure and verify as much data as we can in the field, okay? And so, yes, we can take that data off that drive if we have no other way to do it. And there are manufacturers and drives out there where you may not be able to measure the amperage and the voltage downstream. You just may not have a good place to do it. And in that case, the best case may be that you could take it off the drive. What I tell our folks, though, is if you have the opportunity to measure it, we should measure it. We measure everything else. We have a lot of other controls and things like that out in the field that tell us many other readings that we measure as well. But we typically use our instruments because that's what we get paid for. We get paid to verify those things in the field. And so my stance, and some might not agree with me, is that if you can safely do it, you should verify that measurement. But if you can't, then taking it off of the display of the VFD is certainly a viable option, and it's better than nothing at all. Just what we often say within our company is, if you do that, you need to note that we didn't measure it with our instruments, that we took that off the display of the drive itself. I hope that answers that person's question.
Thanks. This next one, excuse me, I know we're getting technical in here, so there might be a couple of numbers I say. More of a comment, but maybe so you can see your thoughts on this, is asking if you should remind everyone that VFD powered motor is not limited to the nameplate of 60 hertz. NEMA certification allows for the motor to operate at frequencies up to 120 hertz for 1070 and lower RPM motors, and up to 90 hertz for 3400 and higher RPM motors.
No, that's very good information, Sam. I appreciate whoever submitted that, because you're right, we did not cover that today. But it is absolutely correct. NEMA may allow that. Obviously, anytime that you go above 60 hertz, the nameplate rating on the motor, I would challenge anyone that sees that particular instance to ensure that the motor and whatever it's connected to were designed to operate that way. Just because you can run a motor over 60 hertz doesn't mean the fan that's connected to it is rated to go above whatever the 1780 RPM, if it's a 1780 RPM motor. So just because you can do it, by NEMA standards, and the drive will let you do it, doesn't mean it's always a good idea. But the statement that was submitted is absolutely correct. If the entire system is rated to go higher, that is the beauty of drives. You can run them above 60 hertz or that 60 hertz rated speed, as long as you stay within the horsepower ratings of the motor itself, and not exceed those, which obviously would exceed the amperage rating of the motor. And that's something that I know a lot of folks have grappled with as we've moved toward a lot more direct drive equipment, and especially on the fan side. We're seeing a lot of different fan array type technologies that are running, above 60 hertz as designed. And so it's just important for everybody to understand the application and understand the way that the equipment is engineered, and test it accordingly. So thank you, whoever submitted that, because I did not cover that.
Okay, the next one is indirect drive fan. The manufacturer put RPM design on the motor, but on the template of the fan, but on the nameplate of the fan, we found different RPM. Which one of them is a correct one?
Depending upon the manufacturer, normally the equipment manufacturer's tag is going to be the correct designation. Without knowing more information than what you just gave me, Sam, or what was submitted, that's normally the standard answer. We're seeing a lot more, especially on the ECM side of things. And I didn't cover that today because it's a whole different conversation to have. But we're seeing manufacturers that are using especially direct drive ECM motors, and the motor nameplate says one thing, but the way that the manufacturer applies that motor is very different. And so in those particular cases, you have to use the nameplate that's on the outside of the equipment, which is usually an air handling unit, fan coil unit, something like that. And that's, it's an engineered system, so you're going to use the nameplate on the outside of the equipment. I hope that helps.
How can we calculate the actual kilowatts if we don't have the PF and the EFF in the nameplate?
Using that formula that I showed. And so it's not going to be actual, like if you put a power analyzer on it. If you need the exact number, I would encourage you to use an actual power analyzer or power meter. But if you want to estimate it, and it's a very good estimation if you go through the steps that we outlined, you follow that formula, and you can do everything. Obviously, you're going to need a little bit of extra data typically. Those no load figures for the motor. If you follow those steps, you can get there.
Okay, and what is the service factor for motor?
Very good question. So service factor is the ability of a motor to exceed its rated full load amperage. And bear with me, I'm going to run back real quick a couple slides and use that to illustrate that right there, if I can get back through here. So I'm going to bring up that here. We'll use this one here. So if you look here, this is that Baldor information that we had for this example. And you'll notice here that this is full load here. So this will be full load amperage, 17.7 amps, which you'll note we pulled off a nameplate over here. And then we have 125%, 150%, and then we have service factor. Service factor is where the manufacturer essentially says to not operate above this range. Normally, you can operate a motor above 100% and up to the point of service factor. It will diminish the life of the motor in the long run, but motor manufacturers will allow you to do it, and the code will allow you to do it. We always try to suggest to folks not to put things into that application, because you are going to affect the life cycle of the motor itself. And then obviously, if you exceed service factor, more than likely you're going to do permanent and irreparable damage to the motor. Maybe not immediately, but you're going to drastically reduce the service life of that piece of equipment. So depending on the application. So I hope that answers that person's question.
Great. The last question we have here Is there any technology to increase the kilowatt of motor?
That's probably beyond my realm of expertise. That would be something we would need to ask a motor manufacturer. I am not aware of anything that you can just add to a motor that would increase its kW at a given condition. Now, I do know that there are applications, especially in the HVAC industry nowadays, where the motor manufacturers are allowed, they rate their motor off the shelf for a certain condition, but when you put it into a conditioned airstream inside of an air handling unit, they will actually operate their motor. So say in this particular case, we have this 15 horsepower motor, but we're going to put it into an air handling unit in a draw-through application, so it's downstream of the cooling coil. So the motor manufacturer then knows it's always going to have cold air blowing across it. At that point, they may operate that motor to 17.5 horsepower. And so they'll actually allow that manufacturer, the air handling unit manufacturer, to use their motor at an increased wattage, so to speak, because that's what it is, an increased wattage because of the application. But you couldn't pull that 17.5 horsepower motor out and go put it on a central plant, on a pump in the central plant in the same facility and expect it to last at 17.5 horsepower. So I hope, maybe that's where that person was going, but that's the only way that I know you can do it.
Okay, thanks, Justin. That's actually all the questions we have for today. So thank you so much for joining AABC today.
Yeah, let me get back to this last slide, Sam, and I'll turn it over to you.
Thank you so much.
Again, thank you to everybody who joined today. I hope, again, my presentation was worth your time and informative. And you know, we pull a lot of this information out of our training program that we're offering in our training center. So if you'd like to hear any more about that, please visit eabcoinc.com. All yours, Sam.
Okay, thank you so much. Within a week, everyone, you should receive a certificate of attendance. This webinar has been approved for one AIA learning unit. We also encourage you to go to aabc.com and subscribe to our mailings if you aren't already, to get information on our next webinar that we have in our Tab Talk series, the value of Tab to building performance and project closeout. Thank you so much, everyone, and have a wonderful day.
Take care.